Current-carrying conductor in a magnetic field. By the end of this lesson, you should be able to describe what happens to a current-carrying conductor in a magnetic field. Draw the pattern of the combined magnetic field due to a current-carrying conductor in a magnetic field. Describe how a current-carrying conductor in a magnetic field experiences a force. The toy car is moving fast. The electric fan can rotate at different speeds. What enables the toy car to move fast and the electric fan to rotate? The toy car and the electric fan are both driven by electric motors. An electric motor produces force. How is this force produced? A setup consisting of U-shaped steel yoke with a pair of magnetar magnets, a low-voltage direct current power supply, two long uninsulated copper wires, one uninsulated copper rod, AB, and a wooden block has been arranged. Determine the direction of the magnetic field provided by the magnets. The magnetic field is from the north to the south pole. In the setup, the direction of the magnetic field is downwards. Switched on, current will flow in the copper rod AB. Determine the direction of current flow in the copper rod. If the switch is switched on, the current flow in the copper rod is from B to A. What will happen to the copper rod with current flowing in it when placed in a magnetic field? Click on the switch to find out. The copper rod rolls to the right, that is, away from the U-shaped steel yoke. Why? When the switch is switched on, the copper rod becomes a current-carrying conductor. Movement of the copper rod shows that there is a force acting on the current-carrying conductor in the magnetic field. What will happen to the direction of motion of the copper rod if the current flow is reversed? What will happen to the direction of motion of the copper rod if the direction of the magnetic field is reversed? A rod is placed in a magnetic field and connected to the direct current power supply. Describe the magnetic field pattern between the two magnets. Parallel magnetic field lines are formed between the two magnets. The direction of magnetic field lines is from the north to the south pole. Describe the magnetic field pattern for the current-carrying rod. The magnetic field pattern is in the form of concentric circles. Determine the magnetic field direction of the current-carrying rod. The magnetic field direction for a current-carrying straight rod is determined by using the right-hand grip rule. The direction of the current flow is out of the screen. Therefore, the magnetic field due to current flow is in the anti-clockwise direction. How does a current-carrying conductor in a magnetic field experience a force? As the conductor is placed into the magnetic field of the permanent magnets, this results in the combination of the two magnetic fields. On the left of the conductor, both fields are in the same direction, while on the right, the fields are in the opposite direction. This effect produced a resultant magnetic field called the Catapult Field. The resultant magnetic field on the left is denser than that on the right. Therefore, the resultant magnetic field on the left is stronger than that on the right. As a result, a magnetic force is exerted on the conductor to the right, and thus the copper rod is pushed to the right. The force on a current-carrying conductor is caused by the combination of the magnetic fields due to the current-carrying conductor and the permanent magnets. When a current-carrying conductor is in a magnetic field, the conductor experiences a force. How can the direction of the force be determined? Hold out your left hand with the thumb, forefinger and the second finger at right angles to each other. The forefinger points to the direction of the magnetic field, that is, from north to south. The second finger points to the direction of the current, and the thumb indicates the direction of the magnetic force or motion. Thus, when the direction of the magnetic field and current is known, the direction of the magnetic force or motion can be determined. This method is known as the Fleming's left-hand rule. What is the direction of the force on the conductor? The direction of the force on the conductor is to the right. Confirm this by using the Fleming's left-hand rule. Align the hand in line to the directions of the field and the current. What is the direction of the force if the current direction is reversed? When the current flow is reversed, the force on the conductor is to the left. What is the direction of the force if the polarity of the magnetic field is reversed? When the magnetic field is reversed, the force on the conductor is to the right. How do you determine the direction of the magnetic force for the setup? The direction of the magnetic force can be determined by using the Fleming's left-hand rule. Determine the direction of the magnetic force for the setup. Check your answer by clicking on the switch. The magnetic force is to the right. Determine the direction of the magnetic force when the direction of the magnetic field is reversed. Click on the button to reverse the polarity of the magnet. Then click on the switch. Determine the direction of the magnetic force when the direction of the current flow is reversed. Click on the button to reverse the direction of the current flow. Then click on the switch. Determine the direction of the magnetic force when the steel yoke is rotated. Click on the button to rotate the steel yoke. Then click on the switch. What can you say about the motion of the current-carrying rod? Why? The current-carrying rod did not move. The magnetic fields due to the magnet and the current-carrying rod are perpendicular to each other. Thus, there is no catapult field, and therefore no magnetic force is produced.